Okay, this video is for the first in the derivatives unit. So we've already completed the limit unit. Now we're going to talk initially about the limit definition of the derivative. Later on, we'll have more computationally efficient ways to compute the derivative of a function, but for now, we're just going to talk about the limit definition. Occasionally, AP will ask questions that require us to use this definition. So precalculus is mainly concerned with the y value of a function at a given x. But calculus allows us to know how fast the y value of the function is changing at the x, which we call the instantaneous rate of change. So these are two different things. If I have a particular x value like 2, and I plug it into the function and I get 3, then that just tells me that y is 3 when x is 2. But it doesn't give me any information about how quickly that y is changing. Right? On the other hand, it would sometimes be interesting to know if x is 2, how fast is y changing? Right? And that might be a slope value. Like let's say for every one additional x that we plug in, the y increases by 4, right? So the slope of this. So we can't really say the slope of the curve, right? Slope is defined for a line, but we can say that if you were to draw a line tangent to the curve that's touching right at that x value, the slope of that line, as long as it matches the same rate of change as the function curve, we could call that the tangent line. That'll be formally defined as the tangent line. And the slope of that line is what we define as the instantaneous rate of change of the function curve f of x at x is 2. Right, so now we're going to define another word, which is the word derivative. Derivative is, by definition, the instantaneous rate of change of a function curve at an x, and it's also the slope of the line tangent to the curve at that particular x. And each of these x values would have its own slope, like maybe the slope of the tangent line or the instantaneous rate of change of the function, or the derivative of the function is 4 at this location, but maybe down here the slope would be more gentle, so maybe there would be positive 1 would be the derivative value here. Down here the rate of change is 0, and over here we would have negative slopes like negative 1 or negative 4, right? So each individual x value has its own instantaneous rate of change for the function. Right, so we're going to talk about how to compute that value by using the limit definition. So the way this is done is by first saying, well, let's not try to compute the slope around one point, because slope is a change in y over a change in x. So let's start at some general x. We don't necessarily have to define it ahead of time. And then let's go a distance h away to the point x plus h. Then we can plug x in and we'll get the y value f of x. We can plug x plus h in and get the y value f of x plus h. And then we can take this red secant line and draw it between the two. The reason it's called a secant line is that it intersects this function curve at 2 locations, right? And the slope of that would be change in y over change in x. And the change in y is f of x plus h minus f of x. And the change in x is just this h. So this structure here, f of x plus h minus f of x over h, gives the slope of the red secant line. But then what we do is we take the limit as h approaches 0. So as these 2 points get closer and closer together, and then eventually this secant line is so close to 0 here, not quite 0, but the h is so close to 0 that the points are almost on top of each other, and then the secant line has turned into the tangent line. So now it's effectively touching the curve at that one location, and that slope is now the tangent line slope, and therefore we can call it the derivative. So if we take the derivative is going to be equal to the limit as h approaches 0 of the secant line slope structure. And our symbol for derivative is, if the function curve is labeled f of x, the derivative is labeled f prime of x. That's a single quotation, and it's said prime. So that's the limit definition of the derivative of any value at x. And the nice thing about this is it doesn't specify ahead of time what x needs to be. So we could, for example, in this one, have it at x is 1, or we could also just plug in 3. What this is going to give me is some function of x, like say 3x plus 5 or something like that, which means you can plug any x value in and it'll instantly find the slope of the tangent line at that x value. So this is probably the main limit definition that we use. However, there is another limit definition, which is if you've already predefined that you're interested in having this at one specific value, like say f is the x is going to be 1, Then you can say, well, let this just be a constant, like this is 1, and then instead use the x to locate the point that's going to float around here. And then if you plug c in, you get f of c over here, that constant, and if you plug x in, you get f of x. And that means that the change in y is f of x minus f of c, and the change in x is x minus c. And then you can take the limit as x approaches c to get the points to come together. And that's also going to be the derivative, but only at this one predefined value, which means this will turn out to be a number of some kind, right? Not a function, because it already has the x plugged in. Right. So best to see this with a specific example. So we'll take a look at this function here. F of x is x squared minus x, and we'll find the derivative at x is 2. But we'll do it with both those curves just to see how they work. So, or both of those functions. So let's use the more generic one here. F prime of x is limit as h approaches 0 of f of x plus h minus f of x over h. And let's compute that for this function. So what we can do is say f prime of x, we should always label our results here. Let me make the here is going to be equal to the limit as h approaches 0 of, and then there's 2 copies of these functions, this f function. So I like to put those in square braces. And then the function curve is something squared minus something. So I'm just going to copy that pattern here. Something squared minus something, that's the first copy. And then I'm going to subtract another copy, something squared minus something, and that's going to be over h. Okay, then I'm going to go back and fill in, right, for the left copy here, we're filling in x plus h anywhere there was an x. And in the right version, we're going to fill in x here, right? Okay. Then I can go ahead and do some simplifying here. So let me do that. So whenever you write this, you have to identify and label this one time, and then you can say equals again, but then you want to keep writing limit until you eventually actually evaluate the limit. So we're still simplifying here. If I were to try to plug this 0 in here, I would have a divide by 0 situation, which could be undefined, but it might be that we can factor and cancel that h to plug in and find that it's not actually undefined. So we should try to simplify the top to see if we can factor an h out. So if we do FOIL here, that would be x squared plus 2xh's plus h squared. Distributing this negative would be negative x minus h, and then distributing this negative is negative x squared plus x over h. And then we can cancel some things here. So this x here will cancel that negative x squared cancels the positive x. So this is equivalent to the limit as h approaches 0 of 2xh plus h squared minus h over h. And we could factor out an h on the top and bottom now. So let's factor an h out on the top. That would leave 2x plus h minus 1, and then h times 1 on the bottom. This can cancel, so we could factor that out, and that means that this is equivalent to, algebraically equivalent to this. So this whole complex structure is algebraically equivalent to this, which means its limit will evaluate the same. Now, if I evaluate by plugging in 0, I'm not going to write limit again. This is 2x plus 0 minus 1. That's when the limit should go away when you plug in, and that means I have 2x minus 1. So 2x minus 1 there. All right, so let me write the result here. So we have f prime of x, is equal to 2x minus 1. Okay, so now what we can do is we can plug in a particular value, like we can plug in f prime of 2. And that gives me 2 times 2 minus 1 is 3. And if I were to plug in 2 to the original function, which is x squared minus x with 2 plugged in, that is 4 minus 2 is 2. If you were to graph this function, you would see that it looks like this. It's like a parabola. Yeah. And so what that's telling me is if I go to x is 2, and I plug in the function, I get a y value of 2. That's what this number is. But this slope here means that at this location, if I were to draw a tangent line there, the slope of that tangent line would be over 1 up 3. Right? And the beauty of this structure with f prime as an x, since this is a function, that means I could plug other values in. So for example, I could plug in, let's say, -3, right? And that would be 2 times -3 minus 1 would be -7. And f of -3 would be -3 squared minus -3 would be 9 plus, let's see, would that be 9 plus 3 would be 12. So that means if I went to x is -3, this would give me at -3 for x 12 for the y. But the slope of the tangent line here would be for every one we go over, we go down 7. So the slope would be -7. So this structure allows me to plug anything I want in for x, and it instantly tells me the slope of the tangent line at that x location. Right, so that's really the limit definition we use the most if we have to use limit definition, because we can use it then to plug in a bunch of different x's one at a time. Right, but there is another function, another limit definition here, which is slightly different. If you have an older version of the notes, that might be a typo there, but this should say limit as x approaches c of f of x minus c over x minus c. And let's say we want to pre-evaluate this. We know we only want the slope at x is 2, so we'll call that the constant 2. That means that we're going to say this, f prime at 2, so plugging a 2 in, is going to be, by limit definition, the limit as x approaches 2 of f of x minus f of 2 over x minus 2. And that means that we would replace each of these. So the f of x gets replaced with something squared minus something, minus another copy, something squared minus something, over x minus 2. And we would plug in for this first copy x, and for the second copy we're plugging in 2, which means that we can simplify now. So we have the limit as x approaches 2. We can't plug in 2 yet because that would make the denominator 0, but this is x squared minus x, and this is minus 4 minus 2 is 2, so that's minus 2. But this factors into x minus 2 times x plus 1, right? Yep, over x minus 2, which means these x minus 2's would cancel. So that means that we're just evaluating the limit as x approaches 2 of x plus 1, which would then be 3. Okay, and that's what we found on the other one here when we found the generic f prime of x function, and then we plugged in 2, we got the slope 3. Right? But here, if we know ahead of time that we're going to use 2, we can use the simpler structure, which has less work, to get the 3. So the plus of this version is that there's less writing. It's less complicated than this one, right? But the downside is that you can only get the result at x is 2, whereas this one gives me an expression that I can plug in multiple x's to evaluate the instantaneous rate of change at more than 1x. All right. So f of 2, what does that tell you about f of x? That tells you the y coordinate at x is 2. F prime of 2 tells you the instantaneous rate of change, or the derivative, or it can be called the slope of the tangent line. And then we already evaluated these other things here. All right, so does the derivative of a function always exist? The derivative of a function is potentially unique at every x value. So that's possible that there could be some x's where you can't find a derivative. And there are certain things that can cause a derivative function not to exist. One is if the function is discontinuous. So if you have a function that has an asymptote like this, well, there's no place to attach a tangent line. So that's a location where the function, the derivative, does not exist. D and E does not exist. Let's see. That would be one location. Another thing that can happen is if the function's curve abruptly changes instead of moving through. So, like, let's say that you're evaluating what the limits are here. Here's a discontinuity too. So this would be another place where we can't have a limit. Here would be another place where we can't have a limit. You can see why, because like over here, would I say that the slope of the tangent line is this slope, or is it this slope? There's no unique slope there, right? And it has to attach here. So those are locations where the derivative doesn't exist, right? But also this location here, like right here, we could say that the slope here is 0, right? And the slope here might be a tangent line of 1, and the slope over here might be a tangent line of -4. But what's the tangent line right here? Is it this negative slope? Is it this positive slope? Is it somewhere in between? There's no unique slope there. So let me erase that and show you what that is. This is called a corner. Sometimes this is referred to as a corner. Corner. Right, sorry, I'm not writing very well there. Make this a corner. And that is also a location where the limit does not exist. And if you wanted to be really formal about it, you could say the reason why is the limit as x approaches, let's say that's 2, from the left of f of x is not the same as the limit as x approaches 2 on the right. I guess I would have to use the slope derivative. So that would be f of x minus f of 1 over x minus 1. That's not the same as the limit as x approaches 2 from the right of f of x minus f of 1 over x minus 1. In other words, the slope on the left hand, is not the same as the slope on the right-hand side. This is the kind of formal way to show work, to show that that's true. Informally, we can just say wherever there's what we call a corner, which means that we're abruptly changing direction, the slope does not exist there, there's no unique value, and therefore that's a place that's an x value where that's not defined. Here's another corner, so this is also an x value that's undefined. Can you have a slope of 0? Absolutely, right? Definitely. So 0 is fine for a slope. There is one other location though here that's not undefined, and that's this one, because the slope here would be getting close to being perfectly vertical, in which case the slope of the tangent line would have to be an infinity, which is not a number. So this is another place where the derivative is undefined. So the things that cause derivatives to be undefined at a particular x is if the function is discontinuous at that x. If the curve abruptly changes direction, we would call that at a corner. Or if the tangent line is perfectly vertical and the slope would be infinite. Okay, so another thing we might be asked to do is sketch the graph of the derivative curve if we had the function curve. So maybe we could do that by estimating what the slope of the tangent lines are. So let me put some tangent lines in here and just estimate the slopes of those lines. At this location, I would estimate that the slope of that tangent line is 0, and it's 0 here, and it's 0 here, and the slope is 0 at those 3 locations. At this location, if I drew a tangent line in, I would say the slope is about +1. Maybe over here, the slope would be about -1, somewhere around there. This maybe a little steeper, maybe more like -1.5 here, and then -1 here, and then -0.5 there, 0 there, +0.5 for a slope. And then maybe by the time we get over here, the slope is 2. So the slope is 1 about here. And over here, the slope is maybe -0.5. Slope of the tangent line is -1. Okay, if I were to now draw a new function for f prime of x, whose y value is the slope of the f of x curve, then at this location, I would have to make that -1, let's say. So I'll try to use their key there, -1. So maybe -1 about here. Right here, where the slope is 0, would be here. Maybe -0.5 here, +1 here. 0 again by the time we get to here. -1 when we get to here. A little less, and then back to 0 here. +0.5 here. All the way up to +2 by the time we get to here. So I'm thinking that the derivative curve might look something like this. In other words, the y value here of -1 is the slope of the original function line there. And here, where the slope is 0, the y value is 0. So this should actually go through that point, 0 there. Right, so sometimes you're asked to sketch the slope of the f prime graph from the slope of the f of x graph. Right, and then here's another one of those. Let's say we want to graph this. Well, first of all, I can tell a couple things here. There's corners here, and here, and here, and here. So I know this function is undefined. But what is the slope of the tangent line in this location? I would say it's -1. So let's call this -1 down here. That means for all of these values, the slope is -1. And then up here, the slope is +1. So something like that. And then it's -1 for all of these slopes. +1 for all those slopes, -1 for those slopes, +1 for those, -1, +1, -1, +1. And then right at these corners, it's undefined, so I'm going to put open circles there. Your open circles. So this could be the graph of f prime of x, if that was the graph of the function. Okay, so when given a limit expression, sometimes it's helpful to be able to recognize that the limit is actually the definition of the derivative for a particular function at a given x. So here's another type of a problem that we can sometimes see. Let's see here. This is the last, yeah, this is there's only one more example after this. All right, well, looking at this, this 1 could also be expressed as the square root of 1, which really means that we have the square root of 1 here, we have the square root of h plus 1 here. And remember, one of our structures was if you took the limit as, let's see, as h approaches 0 of f of x plus h minus f of x over h, that matched one of these structures, right? That could be the structure for the derivative of whatever this function is right here. And then it looks like there's already been a number plugged into this. So I'm kind of thinking, what if we said this? Let's just say that we're evaluating this. We're evaluating a derivative at 1, since I see a 1 plugged in here. And let me start this over again and rewrite this as limit as h approaches 0. This is going to be something over h. I'm trying to make it match this. And this is like the square root of 1, well, this 1 plus h minus the square root of 1. But let's say that I didn't plug in the x ahead of time. This could be like x plus h and then x here. Then this would be the exact structure we have here. The limit is h approaches 0 of f of x plus h minus f of x over h. And then this f function here, that would just be the square root function, right? So let's see, what are they asking me? Can you determine which function in the given x? Yeah, so this would be the limit definition of the derivative if the function was the square root of x, and we would be evaluating this at the value 1. Yeah, so it's not actually asking me to evaluate the limit. It's just asking me to identify what function is this the derivative of. This is the derivative of the square root function at an x value of x is equal to 1. And this one, let's see, this is the other structure. So we also know that the limit as x approaches some constant c of f of x minus f of c over x minus c is another structure that gives me a derivative of a function. This appears to be the function f of x is cosine of x, right? And it looks to me like we're plugging in potentially, we're evaluating this at 3 pi. So that would be true as long as if I rewrote this as limit as x approaches 3 pi cosine x, and then this should be minus the cosine of 3 pi over x minus 3 pi. So what is the cosine of 3 pi? On a unit circle, we have 1 pi, 2 pi, 3 pi, and the cosine is -1. So this would in fact be minus -1, which is plus 1. So yep, this is right. So this is the derivative structure for f of x is cosine of x if the x value is 3 pi. Kind of esoteric, but we'll see later in this unit why that could be potentially important. And then there's one more structure here. This is the last one, and we're going to just use the limit definition for this. I'm going to go ahead and show you, because there's a lot of fancy algebra here, how to do this for the generic x version, because I think it's more flexible. So I'm going to get a smaller pen here. Let's find f prime of x. Well, it does say find that first, and then find this. So we'll use this version. Limit as h approaches 0. We're going to use this. F of x plus h minus f of x over h. So first, we're going to take our two copies of the function. So this is 1 over the square root of something, minus, and then a copy 1 over the square root of something. I'm going to put x plus h into this version and x into this version, and then it's still over h. It's already quite ugly, fractions within fractions. So there's a couple things we could do, but I'm going to think of it this way. If I have to clear this square root of x, I'm going to do this in 2 steps. Let's just get rid of that square root of x. So what I'll do is I'm going to multiply top and bottom by square root of x. That means when I multiply this in here, that's equal to, change the color, that's equal to the limit as h approaches 0 of, multiplying this across here, it's going to give me square root of x over x plus h minus, and then this is square root of x over square root of x, which is a 1, and then I have an h and a square root of x on the bottom. So that got rid of this fraction inside of the bigger fraction. To get rid of this last one, I'm going to do the same thing, this time multiplying by the square root of x plus h over the square root of x plus h. Because if we multiply that in, we've got the limit as h approaches 0 of, now when I multiply this in, it's going to cancel this off and give me just the square root of x. When I multiply that here, it's going to be minus the square root of x plus h, and then I've got h square root of x square root of x plus h on the bottom. All right, so now can I safely plug in? I can't yet because I still have this h here. All right, so what can we do next? Well, now we've got radicals with something minus something. I'm going to try multiplying by, I'm going to multiply by the conjugate of the numerator. So if I were to say square root of x, but change this to a plus square root of x plus h over, so I just, every time I'm multiplying by something in red here, I'm just multiplying by 1. I'm just choosing to write it a different way. Then the result of that would be limit as h approaches 0 of, multiplying this in, this would be the square root of x times the square root of x. Actually, I'll write it out. Square root of x, square root of x. Then you'll have a square root of x times the square root of x plus h, and then a minus square root of x, square root of x plus h, and then a minus plus, so that's minus square root of x plus h times square root of x plus h over h square root of x, square root of x plus h, and then the square root of x plus the square root of x plus h. Okay, because this is the conjugate structure, that means there's going to be some canceling. These middle terms will always cancel, and then that means that the result will be limit as h approaches 0 of square root of x times square root of x is square root of x squared, which is just x. And then we've got minus, and then square root of x plus h times square root of x plus h is an x plus h. And then I've got h square root of x, square root of x plus h, and then the square root of x plus square root of x plus h. Okay, distributing this, the x's will cancel and leave a minus h on the top. So I'm going to write this again. Limit as h approaches 0. We have a negative h on the top. which I'm going to factor out, leaving a 1 here. And then I'm going to factor this h out of the bottom. That leaves the square root of x plus h, square root of x plus square root of x plus h. And that means that this h and this h cancel. So going up there, the limit as h approaches 0 of, we've got a negative 1 now. And on the bottom we have a square root of x, square root of x plus h, square root of x plus square root of x plus h. Okay, now it's safe for me to plug the h in, 0 in for h. So I'm not going to write the limit anymore because I'm plugging in now. Negative 1 over the square root of x, square root of x plus 0. I'm plugging the 0 in for that h. And then I have square root of x plus square root of x plus 0, which is the same as negative 1 over square root of x times square root of x, and then this is square root of x plus square root of x, which is negative 1 over square root of x times square root of x is x, and then in here this is going to be 2 square root of x's. So it looks like the result is negative 1 over 2 times x times the square root of x, if I did that right. Yes, okay. So that's the general expression for f prime of x. Now in the second part of the problem, they're asking me to find this for a particular function, f of 1 and f prime of 1. So let's find f prime of 1. That's negative 1 over 2 times 1 square root of 1, which is negative a half. Whereas f of 1 is, here's the original function, 1 over the square root of 1 is 1. So this is the y-coordinate, and this is the slope of the tangent line. It could also be called the derivative, or you can call it the instantaneous rate of change of the f of x curve at x is 1. All right, a lot of careful algebra here, but yeah. So thankfully, starting in the next section, we're going to learn a much faster and more computationally efficient way to find the derivative, but the limit definition always works. This is the fallback method if none of the other methods work. All right, that's it for this video.